two types of 6-bar mechanism. One is named as Watt 6-bar linkage. So it's more like a symmetric configuration. So you have 2 bar on the left, 2 bar on the right-hand side, and there's a triangular or a 6-joint link at the center. And there's another type, it's called Stephenson. So the difference is this one, well, it's not symmetric. So I have 1 bar attached to one end of the triangle, the other bar attached to the other end of the triangle, and the other 2-bar linkage connect to the other end. And we saw this video last time. Let's just play one more time. So this one is a Stephenson's 6-bar linkage, or it's also called clan. It's blocked there. It's also called clan linkage. It's one type of Stephenson's 6-bar mechanism. And let's play first. So you can see the motion of this end. It's moving in more like a triangle trajectory. So the purpose we mentioned last time is this mechanism, we want to use it to mimic the trajectory of an animal or a spider foot. Yeah. To make it more like a real footstep. So the purpose we use a 6-bar mechanism. You actually can also use a 4-bar mechanism to do something similar, but in a 4-bar mechanism, you don't have so many parameters to fine-tune the trajectory. So usually we use this mechanism to perform this type of motion. And I mentioned it's 6-bar mechanism, but it may not be so clear. So if you pay attention to this one, I can't find my mouse. Let me play one more time. Okay. So I'll stop here, and I say it's a Stephenson's mechanism, but it may not be so easy for you to see it. So for Stephenson's mechanism, we have 3 joints connected to the ground, which is these 3. So this red one belongs to the same link. The one in the background, this dark red link, is connecting to this 3 bar. And we consider this one as ground because this one is not moving at all. This red one is dark red one. So this one is the ground. And there's one link here, one link here, and one link here. Yeah. And remember in Stephenson's mechanism, there's a triangular bar or a 3-joint bar, which is this one. But in this case, it's more like just a straight bar. But it has 3 joints, which is this 3. So instead of a triangular link, in this mechanism, in this clan linkage, we use more like a straight line, but you also have 3 joints connecting to other bars. So it's similar to the Stephenson's mechanism. Just for you to compare the 2 mechanisms. So in this one, we have not a triangle bar, but not triangular bar, but it's a straight line. It's to replace this one. Yeah, you also have 3 joints, and the same as this one has 3 joints. But just an extremely case, you make this triangle become a straight line. And there's a short bar here, which is representing this one and this one. Or you can compare to this one. And this one is a 2-bar mechanism, connecting 2 bar and connecting to the 3 joint bar. Yeah. But this one extends this bar a little bit longer. So this one belongs to the same one. It's a rigid body. There is no joint between this one and this one. So it's like you extend this one, but this one is rigid. So use this point as the output. And you can tune the length of this one to make the trajectory change. Depends on your application. Maybe you want the trajectory more like a triangle or more like a straight line. So here is an example. This mechanism is installed. I can't find my mouse again. This one, you just install 4 sets of the clan linkage. So to represent 4 foot of an animal-like robot. And you can perform this type of trajectory. It's more like a real animal's motion. And of course, you can install on it's a spider. It's still using this clan linkage and to perform some motion more like a real spider. I don't know. I think it's more like a spider. But you may wonder why they don't want to just use wheel instead of using this mechanism. Is there any advantage to use this one? Well, I can simply just use a wheel if I just want to make this robot move. Why do I want to use this mechanism instead of using wheel? You can see it's so slow. Although it can do some complicated motion, but it's very slow. But what's the advantage to use this one instead of using wheels? Because it looks cool. I think it looks cool. Is there any other reason we use this one? Or why we want to mimic the animal or human motion instead of just using a wheel? Well, imagine in a very rough terrain. I mean, if there are some rock on the road or the road is not so smooth, well, sometimes you may need to cross some obstacles. So if you use this type of mechanism, you see we can lift the foot to cross certain obstacles. Yeah. So I think that's the main purpose to use this more foot-like mechanism instead of using wheel. You can use it in a more, you can use it to climb the stairs or something. Any questions? So it's just an application to use this 6-bar mechanism. I think this is the most commonly seen application for this 6-bar mechanism. So you can, sometimes you may not want a trajectory in this way, so you can try to change the dimension or change the length or change the angle of these bars and to change the output. But it depends on your application. So if we want to find this trajectory, and maybe also the velocity and acceleration is your concern. Because sometimes you may want the trajectory to be very smooth instead of accelerating at a certain point but de-accelerating in a certain point. You may also want to change the acceleration through this trajectory. So if you want to know the velocity acceleration, you will need to perform the velocity and acceleration analysis we have done in the previous examples. So once you have this mechanism, you can just apply the method we introduced previously and to try to find their velocity and acceleration and also a position. Any questions? Okay. Then we'll move to the second part of a graphical analysis. So the difference between this part, I think this one is in the chapter 5 of your textbook. We're still using the graphical method to perform the analysis. And there's another method we'll introduce later. It's called analytical analysis. And for analytical analysis, we'll just use pure math. So we'll just write down some equation and to manipulate those equations to find a solution. Right now in graphical analysis, we usually draw something. We usually draw the vectors, the velocity or the acceleration vectors, and to help us to perform the analysis. The difference between the second part. In the first part of the analysis, we usually deal with maybe this type of examples. So we usually deal with, for this type of link, if it's not slider, we always consider the length between O and A, or in this case for sure, O and A, the length of OA is not going to change. But, so this bar, if I call it bar 2, bar 3, bar 4, bar 2 will only rotate. So when we calculate the velocity, or let's say velocity first, velocity will only be in this direction. We won't have any velocity in this direction. We won't have any velocity along this OA line. That's for this this type of link. Yeah. Velocity is always in this direction. There's no component in this OA direction. Let's see another case. Let's see this OB. If we consider the distance, the displacement between OB, or the velocity of OB. For OB is another case. The direction or the orientation of OB never change. It's always in this direction. This OA is going to change because it's going to rotate, but the length is not going to change. So this one, direction will change, but the length This one direction will change, but length is fixed. Just write fixed. This for bar 2 or for OA. But for OB is another story. For OB, the length is going to change. But the direction is not going to change because it's always in this direction. This slider can only move in this way, so the result is OB is always in this direction. It's always horizontal. Fixed. Varied length. Direction. So it's either, so in the previous example, there's only one variable. In this case, the variable is the direction. In this case, the variable is the length. We never deal with the problem, both the direction and length are changeable. So that's what we are going to deal with in the second part of the graphical analysis. So consider this case. Well, it's actually assembled by three links. So there's a grounded link, and there's a link 2 is a gray one, and the pink one is the third link. But we are considering the length OP. O is a fixed point, and P is on the slider. So if we consider the OP, either the position, velocity, or acceleration, you see that because the slider can move within this slot, so the length is going to change. But this bar can also rotate, so the angle will also change. So in this case, if we consider OP, the length is going to change. It's possible that the length is going to change and the direction is going to change as well. So this will be a more complicated case. So in this case, if we want to consider velocity, the velocity may have a component in this OP direction and may also have a component in this tangent direction. So this one may have two components, may have a normal component and also a tangent component. And if this one has two components in velocity, you'll have more components. You'll have 4 components in the acceleration plot. So we'll try to figure out what's the extra 2 component in this new case. So in order to understand what's the extra component, we'll go back to the math first. I think it's easier to understand that in the math. So for every vector, here I start with position, so I represent as R. So RPO is representing the relative displacement between this P and point O. And here I try to use a vector to represent everything. So this RP is representing the position, and I'll use VP and APO. So for velocity and acceleration. For every vector, I can represent in this way. I use in the imaginary coordinate. So this means so I represent the x-axis as a real coordinate, and the y-axis is the imaginary. So you can use any other way, but here I just would like to use this coordinate to represent this vector. And this one is a vector, and this one is the scalar. So this one has only value. There's no vector information in this one. I put the vector information here. So this I means in this direction. And if there's no I for this cosine, so that's for the real part. And this for the imaginary part. So it's like this. Any question for this representation? And of course, you can use any other coordinate. I think this one is the simplest one. Yeah. And so we can represent any vector in this way. I represent this displacement, and it's actually RPO and times cosine theta p plus I sine theta p. So what if this one is the displacement? Well, this one can be either absolute displacement or the relative displacement. Depends on if O is fixed or is movable. But, well, this one is universal. You can use it to represent any relative displacement between 2 points. This O can be fixed or it can be moving. So this one is displacement. If we know the displacement can be represented in this way, then what would be the velocity? Velocity is simply the time derivative of the displacement, right? Yeah, so we can differentiate this one by time. So I'll just write down first. So I do the time derivative of the displacement, and we can find this new, stand here. Let's see this new representation. Well, we basically just try to do the differentiation for every term. So I didn't assume which one is differentiable, which one is not. So I just differentiate everything here. So maybe this R is differentiable, so I do this part first. R dot times the cosine theta p plus I sine theta p. So let's you do a time differentiation for the first part. And maybe this theta is differentiable, it's changing. So you can also keep this RPO and to do the differentiation for this part. So you will get the theta p dot and times cosine, the differentiation of cosine is sine, is minus sine. Yeah, minus sine theta p and plus this differentiation of sine theta p will be cosine. So in this velocity vector, we have two components for now. Previously, we have either this one or this one. That's because either we fix this r. If we fix the r, so I'll just erase the example. So for this type of link, because the length is not going to change, so the r is going to be a constant. So this term will disappear, will become 0. Yeah, when you do the differentiation over time. And the second part is r times theta p dot. For this slider, because the angle, or if you consider OB, because the direction of OB never change, so the theta for OB never change. So in that case, we won't have this component. The theta p dot is going to be 0. So that's why in the previous examples, we either have this one or have this one. Well, that's because we only consider either r or theta is a variable. Only one of them is a variable. The other one is a constant. But here we just assume both of them are variable. So here we will keep these two terms, these two components. So one thing to notice, you may see this one is cosine plus I sine. This one is a unit vector. This one is also a unit vector. And the difference between this one, if you draw them in this plot, you'll find these two, they are perpendicular. So if cosine theta p is in this direction, and cosine theta p plus I sine theta p is in this direction, this minus sine theta p plus I cosine theta p will be in this direction. And they are perpendicular. Any question for this one? And then we'll move to the acceleration part. So we'll just keep doing the time derivative for the velocity. So if we keep doing the time derivative of the velocity, we'll have so many terms in the acceleration. So here, well, you just do the differentiation for each terms. So you'll see the first term is we have this r double dot and p slash o and this cosine theta p I sine theta p. And we'll also have this term, this 2 time. This one comes from if you differentiate this r, and you'll get this, the very first component of the acceleration. And if you differentiate the theta for this first component of velocity, you will get this one. But you will get another exact the same one by differentiate this r in this one. So that's why here there's a this term need to be times by 2, because either you differentiate this one over the theta, or you differentiate this one over r, you'll get the same thing. So you'll times 2 here. So let's just keep doing, and if you differentiate the theta here, the theta dot here, you will get the theta double dot, and the unit vector is the same. Also, final one, you differentiate the last part, then you will get this RPO and theta p, because you will get a theta dot from differentiation of this one. So this one, RPO theta p double dot, RPO theta p dot square times this unit vector. So right now we have 4 components, and we'll name them. This one, previously we have 2 components for the acceleration. Do you recognize which 2 we used before? 2 components we have used in our previous examples. If you remember, one is the tangent component, and then one is related to the angular acceleration. So it's this one. The theta p double dot is alpha. So we have this alpha r and the direction. So this one is the tangent component we used before. And we have another component, the centripetal or the normal component. It's related to omega square. So it's this one. This one is omega square r. So these new terms, these 2 components are new. This one we call it sliding. Yeah, because it's in the sliding direction. It's the differentiation of the theta, of the length. So it's in the sliding direction, and the direction is the same as original link direction. So this one means if my vector only the length change, then we may have this component. We actually have this one before when we analyzed this example, but we just didn't mention it. Yeah, we just give it a name, is a sliding component. Because when we analyze this one in the acceleration, it has only one component, which is in the horizontal direction. And at that time, we didn't name it, but it's actually this one. And this one is, we call it Coriolis. It's 柯氏加速度. So we have 4 components, and this one, each of them can be represented in another way. Well, this one will just stay in this way. And this one previously we'll write as, let me think, we can represent this term in this vector by this vector. It's the alpha. Suppose I have a bar. Because a component in this direction, so this one can be represented this way because it's alpha cross R. Alpha is pointing, if I join this way, alpha is pointing out of this board, and R is in that direction. So alpha cross R will be in this direction. So you can either use this one or this one. And this one, if you pay attention to these two, this R dot can be represented as a, because this one is a linear velocity, because the length is changing, so it's not related to omega. It's about a linear velocity. So if you represent this one in vector, it's V, yeah, it's a vector B. And this theta P is related to this omega vector. So either this way or this way. Well, depends on if you want representing a cross between two vectors, or you just want a more exact expression. That's up to you. Any question for this one? Yes?
This component, what is it used for?
Useful?
Yes. Why do we use them?
Why do we use them? Because they will appear when the link is more complicated. Yeah.
If we look at this graph,
Yes.
why do we need this component of acceleration?
If we don't include those components, then it's not enough to express the motion of this link. Yeah. Because previously we only have this, either the length is fixed or the orientation is fixed. At that time, we only have a few components of these four. But right now, if we consider maybe the length is going to change and the orientation is going to change as well, then that's the most, with most components, then there's gonna be this case. That's the most extreme case. We may have 4 components, but usually it's not so complicated for this one because it has only the theta dot, there's no R dot. So this one will disappear, this one will disappear, will become 0. So you have only these 2 components. But in some cases, we may have all of them. Yeah. So any questions? Yeah, and let's take a look of the direction. You will see some of them. We actually have only, I don't know if I should say 2 direction or 4 direction, but they are all perpendicular. So here just, this figure just draw every component, 4 component. And well, let's look at this one. I think it's better to look in this one. For this one, well, we start with the easy one. So this one is the centripetal component. We know this R is always positive because it's the length. There's no vector here. So, and there's no minus length. So this one must be positive, and this one is theta dot square. Because it's square, so this one is always positive. So the only component that decide the direction is the unit vector. It's this minus cosine theta p minus this high sine theta p. And if you compare this one as the original one, well, basically the difference between them is if one is pointing to the left, another one is pointing to the opposite direction. So this component is always pointing to the reverse direction of this one. So if this one, if my original unit component is pointing this way, and the centripetal component, yeah, or the normal component is pointing this way. And the tangent component. Tangent component, well, tangent component might be different. We know this one is always positive, but this one could be positive and could be negative. So you may have plus or minus sign here, and the unit component in this one is the same as this one. But because this theta double dot, it's gonna change the direction. If this one is minus, you will going to change the direction in the reverse direction. Yeah. So this one is either pointing to this direction or pointing to the other direction. It depends on the sign of this one, or theta p double dot. Yeah. So you need to pay attention to the direction of the acceleration because it's going to change the direction of a tangent component. Yeah. By either this way or this way, we know it's always perpendicular to the original one. Original, I mean this RPO. If RPO is in this direction, and the tangent component is always in this perpendicular direction. But I don't know if it's this one or this one. It depends on the direction of the angular acceleration. And the sliding. The sliding, well, this one could also be, it can be positive, it can be negative. Because it's the rate of the change of the velocity. Yeah. This one could be positive and could be negative. If you see the unit vector, it's the same as the original displacement vector. So for this sliding, it will either be this direction or this direction. Either way is possible. Yeah. But I know it must be along this original displacement line. Yeah. And the final one is this one. This one is R could be negative. It could be positive. And the theta p, yeah, it could be positive or negative. So this one would, the R dot and the theta dot, they both can decide the direction. And we take a look of this, this unit vector. It's the same as this one. So we know the Coriolis component is either in this direction or in this direction. So this one is the same as the tangent, but well, might be in the opposite direction, depends on the sign of this R dot and theta p dot. And the sign of this theta p double dot will also decide either is this way or this way. So the direction is not always in the same as this one. It may change. Only the centripetal is always pointing to this direction, but the rest, well, they might be reversed. Yeah, they don't always point into totally different direction. This Coriolis may have chance to have the same direction as the tangent. But they can only be perpendicular to this direction. The Coriolis and the tangent is always on this line. Direction might be changed, might be opposite. And this slip, this S component, can be either this way or the same as the centripetal direction. So we'll need to pay attention to the sign of those terms, because they will decide the direction. Any questions? So the same as previous cases, we'll use several big. So this one has 4 components. So to represent this AP or APO, right now O is fixed. So you just ignore the O. Well, AP is the absolute acceleration. So it's a combination of all the 4 components. There's a tangent component and slip or sliding component. There's a Coriolis component, and there's a normal or a centripetal component. So combination of these 4 components will be the resultant acceleration of point B. Yeah. So for the analysis, there won't be much difference, but we will have more components to figure out. Yeah, so that make the analysis more complicated. Okay, so I think that's it for today. And yeah, I'll see you next Monday. So we'll have exam, and the exam won't include this part. It will just, so it's only the chapter 1 and chapter 4 in your textbook. Yeah. We won't include the slip and Coriolis acceleration or the velocity. Okay.